Welcome. This is the video for section 6.7. We're going to be doing partial fraction decomposition. Partial fraction decomposition. So in the past, you have taken fractions like this, and you've discovered that the common denominator would be x minus 3 times x plus 4. Then we multiply the top of this one by x minus 3 and the bottom by x minus 3. And multiply this one by x plus 4 top and bottom, and then we push the fractions together so that we have this. And then we simplify the numerator, and we come up with this fraction right here. Well, today what we're going to do is we're going to reverse this process. We're going to take a fraction, and it has to be a proper fraction. Okay, in order to do partial fraction decomposition, you have to have a proper rational expression, a proper fraction. It has to be a proper rational function, which means, let's do a little quick review. The top has to be a smaller degree than the bottom. So on this one, the top is degree 1, the bottom is degree 2. That makes it a proper rational function. We can only do this partial fraction decomposition if it is a proper rational function, okay? And what we're going to do is we're going to take a fraction, a single fraction, and we're going to pull it apart as a sum of simpler fractions. Okay, so this process is called partial fraction decomposition, and the simpler fractions are called the partial fractions. Okay, so that's our goal today. So we're going to go through some cases, and case 1 is when your denominator has only non-repeated linear factors. So an example is going to be like this one. Notice there's a linear factor here, there's a linear factor there, but they are different. Okay? So non-repeated or different linear factors. Okay? Linear means degree 1. So here's the process that we go through to write a partial fraction decomposition. You have to make sure your denominator is factored completely. You set the fraction equal to the sum of multiple fractions, one for each factor in the denominator. You clear the equation of fractions. You can choose nice values, and we're going to do this a lot. Choose nice values of x to solve for a, b, c, however many you have. If that's not possible, you equate coefficients, write a system of equations, and then solve for these constants a, b, c, however many there are. And then you rewrite your fraction with the constants a, b, and c, whatever we have in place. And we'll do examples to clarify all this. So example 1, we are going to do a partial fraction decomposition for 5x minus 1 over x plus 1 times x minus 2. So the first step is we're going to take this one fraction, so it's a single fraction, and we're going to write it as a sum of two fractions, one with the denominator of x plus 1, one with the denominator of x minus 2, and these a and the b represent unknown constants, and our job is going to be to find those constants. So this is step 2. Set the fraction equal to a sum of multiple fractions, one with each factor as a denominator. So we've got two factors, so we've got two fractions. If we had 3 different factors, we'd have 3 different fractions. But we're also talking here about linear factors. Okay, so our factors are linear, which means degree 1. Both of them are degree 1. So now the next step is step 3, clear the equation of fractions. So what we're going to do is we're going to multiply both sides of the equation by a factor of x minus or x plus 1 and a factor of x minus 2. Okay, so notice what happens. If I multiply the left side, so I'm multiplying both sides by, so in this step 3, we're going to multiply both sides of the equation, because remember we have to multiply both sides by the same thing to maintain the equal sign. So if I multiply the left-hand side, I just have the numerator. When I multiply the right-hand side, because of this plus sign in the middle, I have to distribute this factor or these factors to both fractions. So the first time I just multiply this. So it's like I have this, okay? And I have to distribute this to here and to here, okay? So when I multiply the first fraction by that product, the x plus 1 cancels, and I have a times x minus 2. Second time, when I multiply the second fraction by that common denominator, I have the x minus 2 canceling, and I have b times x plus 1. Okay, now we're going to choose nice values of x to solve for a and b. We only have a and b to work with. So what are the nice values of x? Well, the nice values of x, so the nice x values, we'll put quotes around that. The nice x values are going to be the ones that make these factors equal to 0. So if x plus 1 equals 0, we have a nice x value. And if x minus 2 equals 0, we have another nice x value. Okay, what we're going to do is we're going to plug those in. So over here, I'm going to plug in x equals -1. So if I do that, what I have is 5 times -1. I'm just going to plug it into this equation, the equation there in red. Okay, and on the other side of the equation as well. So we have 5 times -1 minus 1 equals a times -1 minus 2 plus b times -1 plus 1. Well, the reason this is going to work nicely is this is going to be 0 right here. -1 plus 1 is 0. 0 times b is still 0. So that goes away. And in the future, I won't even write that last one. The one that's 0, I won't even write it. So this is -5 take away 1, which is -6. This is -3 times a. So -1 take away 2 is -3. Then I'm multiplying that with a. So I divide both sides by -3, and I have the a equals 2. Right? Divide both sides by -3, a will equal 2. Okay, so there's the a value. Now I'm going to take the other nice value of x, which is x equals 2, and I'm going to put that into the same red equation up there. So I have 5 times 2 take away 1 equals, when I put a 2 in there, 2 minus 2 is 0, 0 times a is 0. That one goes away. And then I have b times 2 plus 1. That's 10 take away 1, which is 9, equals 3b. Divide both sides by 3, so b is 3. 9 divided by 3 is 3. And then that is step 5, or 4. We chose nice values. We solved for the a and the b. We don't have to do step 5 because we've already found all of them. So our last step, step 6, is rewrite the setup from step 2. So this setup that we have right here, this setup right here, we're going to rewrite it with the a and b in place. Okay, just scroll down far enough that I can see that. So what I'm going to do to finish it up, I'm going to rewrite my setup 5x minus 1 over x plus 1 times x minus 2. That's going to equal a, which is 2 over x plus 1, plus b, which is 3 over x minus 2. And that is our final answer. Okay, moving on to the next example, next page. Example 2, resolve the rational expression into partial fractions. Well, what you first have to do is you have to factor the denominator. Okay, so if you've forgotten how to factor, I'm going to go through this really fast. And if you remember how to factor, just do the factoring and skip this part. So we look for a GCF, doesn't exist, or it's 1, I should say. The GCF is 1. We do a times c. 2 times -1 is -2. I look for 2 factors of -2 that add up to -1. That's what I need for my sum. So only factors of 2 are 1 and 2. If I make that a positive 1 and a -2, those will add up to -1. Then I do a quick little box. I'm going to go through this fast. We have 2x squared. Middle term gets split into a 1x and a -2x. And the last term is -1. GCF for the first row is x. GCF here, we're going to do a -1. And if you use grouping, then do grouping. This is 2x for that column, and this is 1 for that column. So our denominator factors as x minus 1 times 2x plus 1. So that's a 2x plus 1 right there. So we're going to take that denominator and we're going to factor it as 2x plus 1 times x minus 1. And we have two different linear factors. So we have a constant over the first of the linear factors plus a constant over the second linear factor. Okay, I'm going to fix that x a little bit because I'm not real happy with that. Okay, now we're going to clear out the denominators by multiplying both sides by a factor of 2x plus 1 and a factor of x minus 1, right? We're going to multiply both sides by that. So on the left, we get x plus 5. On the right, we have a times, well, let's see, when I multiply the first fraction, then 2x plus 1 cancels, and I have the x minus 1 remaining. When I multiply the second fraction, okay, because we have to distribute that, multiply that fraction, the x minus 1 cancels, and I have b times 2x plus 1. Okay? It's just a matter of multiplying both sides by that denominator that we have right here. Okay, now we're going to look at the nice values. So if x minus 1 equals 0, we have x equals 1. That's going to be easy to work with. But this one, I solve that for x, I get x equals negative 1/2. I'm not sure I think that's a nice value, so I'm going to show you a little different way we can do this one. But I am going to use the x equals 1 because it's nice. So if I work with the x equals 1, so this one's not so nice. So if we decide it's not so nice, we'll just do a different method for finding the other constant. Well, the x equals 1 is going to allow us to find b. Look what we get. 1 plus 5. We replace the x with a 1. We get 1 plus 5, which is 6, equals, on the other side, 1 take away 1 is 0. So this first piece disappears. That turns into 0. Right? So we have b times, let's see, if we plug in a 1 for x, we have 2 times 1 is 2. 2 plus 1 is 3. So we have 6 equals 3b, or b equals 2. Okay? Now, what I need to do is find a. But I don't really want to work with the x equals negative 1/2 because then I have fractions. I'd rather not work with those. So I'm going to pick another nice value that might work well, and that would be x equals 0. Because I already know b, this is going to work out great. Watch what happens. If I replace the x with 0, I have 5. So I'm replacing in this equation right here each time. So I have 5 equals, and if I replace the x with 0 on the other side, I have a times negative 1 plus b times positive 1. Or in other words, 5 equals negative a plus b. But I already know that b is 2, so 5 equals negative a plus 2. Solve that for a. What do we get? We get negative a equals 3, so a equals negative 3. Okay? And then the last step for this is to rewrite our equation, or rewrite the red starred equation. Oops, not that one. This one. Rewrite this equation with the a and b plugged in. So we have x plus 5 over 2x plus 1 times x minus 1 equals, I'm going to replace the a with negative 3. Negative 3 over 2x plus 1. And then plus, replace the b with the 2. 2 over x minus 1. And there's our answer. Okay. Now we're going to move on to a different case. What happens if the denominator has repeated linear factors? So still linear factors, but what if I have repeated linear factors? So an example is right here, where we have the factor x plus 1 twice. That's a repeated factor. So x plus 1 times x plus 1. Like it says, solving is very similar to case one. However, you need to deal with the repeated factors with multiple fractions. Let me show you what I mean by that. So if I have x plus 1 twice, that is going to give me 2 fractions. Let me show you what I mean. We have 5x minus 1 over x plus 1 squared. We have to have an a over x plus 1 to the first power and a b over x plus 1 to the second power, where a and b are constants. Okay, that's the way this is going to work. So what we're going to do is now we're going to go through the same kind of process. We're going to multiply both sides by x plus 1 squared. So if we multiply the left side by x plus 1 squared, we only have the numerator. We multiply the right side. When we multiply the first fraction, this fraction right here, one of the factors of x plus 1 is canceled and the other one survives. And then we have that. Now think about how that worked. I'm multiplying this by x plus 1 squared, and I have to distribute that. Okay, so the first time I have 2 factors of x plus 1, only one's going to cancel. And the second time, they both cancel. All right? Think about how that algebra works there. Okay, so now, do we have a nice value of x? A nice x value? Yes. If x plus 1 equals 0, x would be negative 1. That's going to cause the factor x plus 1 to disappear, to turn into 0. So we're going to plug in x equals negative 1. So we'll have 5 times negative 1 take away 1. That's negative 6. Feel free to skip a step here and there. When we plug negative 1 in here, negative 1 plus 1 is 0, so that goes away. And all that's left is the b. So we have b equals negative 6. Okay. Now we'll go after the a. I don't have another value of x that's going to make one of these factors go away, but remember what we did last time. We can do this again. If we plug in x equals 0, 5 times 0 is 0. We're plugging it in right here into this equation. Replace the x with 0. 5 times 0 is 0. Take away 1 is negative 1. And on the other side, we have a times 1. Because if I replace the x with 0, 0 plus 1 is 1. So I have a plus b. But we already know that b is negative 6. You can write it as plus negative 6, or you can write it as subtract 6. So if I add 6 to both sides to zero that out, we get the a equals 5. Okay? And then our last step is to rewrite this equation right here with the a and b replaced with the numbers that we found. So 5x minus 1 over x plus 1 squared will equal 5 over x plus 1 and plus negative 6 over x plus 1 squared. Now, the discerning student would notice that, or if we understand the algebra, I can move that down here and make that a subtraction if I would like to. So either plus or minus, whichever way you want to write it, should work out. Okay. We do this because in calculus, a lot of times to do integration, we need to split fractions, decompose them so that we can work with the simpler pieces. Okay, let's flip to the next page where we're going to do example 4. We have to do some factoring in that denominator. So notice what we're trying to do. We're trying to resolve the rational expression into partial fractions. In other words, find the partial fraction decomposition. In order to do this, first thing we have to do is factor the denominator. So notice what we have is we have a common factor of x that we can take out. So we have x times x squared minus 2x plus 1. And then the x squared minus 2x plus 1 will actually factor as x minus 1 times x minus 1, or x minus 1 squared. So notice what we have. We have a factor of x, and we have a repeated factor of x minus 1 because it's there twice. So what we're going to do as we decompose this, we're going to have a constant divided by x, plus we have to have two fractions for that x minus 1 squared. We have to have a b over x minus 1, and we have to have a c over x minus 1 squared. Okay, next step, we're going to multiply both sides by this function to clear the denominators. So on the left, we'll have just the 3, and on the right, we'll have a times the x disappears, and I have x minus 1 squared. When I multiply that second fraction by this piece that's underlined in red, the x is still there, but only one of the x minus 1s. And then when we multiply the last fraction, this fraction right here, when we multiply that fraction by this, okay, what do we have? We have the x staying, and the x minus 1 squared is gone. Okay, we've got a couple nice values of x that we can work with. Nice x's are going to be x equals 0 and x equals 1. The ones that make my product there equal to 0. Okay, so I'm going to plug in x equals 0. This is going to be 3. But on the other side, I have a times, well, if we replace the x with 0, I get 0 take away 1 is negative 1. Negative squared is 1. So I have 1 times a. So that's just a. Think about that. Oops. And this disappears because when x is 0, that's gone. And this disappears because c times 0 is 0. So a is 3. Well, that worked out nicely. Now let's see what happens when x is 1. Plug in x equals 1. The left side is still 3. This piece turns into 0 because 1 take away 1 is 0. 0 squared is still 0. 0 times a is 0. So the a is gone. If x equals 1, let me underline in green. That one is 0. So these first two pieces turn into 0, and I have 1 times c. So c is 3. Oh, this is working out so well. Now I have to find b. And how am I going to do that? This is a little tricky. So this time, what we're going to do is we're going to equate coefficients a little bit, I think. Actually, no, you know what? Let's plug in another value. We'll do equating coefficients a little bit later. Let me plug in x equals 2. That works pretty well. Left side is 3. What's the right side? If I replace the x with 2, 2 take away 1 is 1. 1 squared is still 1. So that's just a, because it's a times 1. Plus, replace the x with 2. I have 2 here. 2 take away 1 is 1, so I have 2b. And then replace the x with a 2. I have 2c. But notice I already know what a and c are. So that equals a is 3. B I do not know yet. But if c is 3, which it is, c was 3. 2 times 3 is 6. Okay, what do I have? I have 3 equals 9 plus 2b. Subtract 9, we get negative 6 equals 2b, so b is negative 3. B equals negative 3. All right, and then our final step, our final thing to do here is rewrite the fraction as a over x, a was 3, plus b over x minus 1, b was negative 3. So I think instead of writing plus negative, I'll just write that as minus 3 over x minus 1, and then plus c over x minus 1 squared. And we're done. Okay. All right, now we're going to look at case 3. What if the denominator has a non-repeated irreducible quadratic factor? Remember what an irreducible quadratic is. It's a quadratic of the form ax squared plus bx plus c whose zeros or whose roots are not real. In other words, they have to be written in terms of I. All right, non-real zeros, non-real roots. Okay, so an example of an irreducible quadratic would be x squared plus 1. Another example of an irreducible quadratic would be x squared minus x plus 1 that we're going to run into a little bit later on. Okay, roots that are not real. Okay, so what we have to do in this case, you have to put a fraction in like this. There's your irreducible quadratic in the denominator. Notice what my numerator has. My numerator has a linear term, a linear polynomial of degree 1, at least potentially degree 1. Okay, so what we're going to do is we're first of all going to rewrite this. Here's what it needs to look like. So there's my x minus 2. There's my irreducible quadratic x squared plus 1. We have to have a constant over x minus 2. We have to have a bx plus c over x squared plus 1. And then the rest of it is very similar to what we've already done. So we're going to multiply and clear denominators. So we're going to multiply both sides by a factor of x minus 2 and a factor of x squared plus 1. So on the left, we just get the numerator. On the right, we have this. Parentheses have to be there. It has to be that bx plus c times the x, whoops, not the x squared, the x minus 2. Because the x squared plus 1 will cancel. Remember what we're doing? We're multiplying both sides of this equation by x minus 2 and x squared plus 1. But because of this plus sign in the middle, we have to distribute. And we have to be doing this on both sides of the equation, because whatever we do to one side of the equation, we have to do the same to the other side. Okay? So we get this equation right here. Now, we do have one nice x value. We have x equals 2 that we can use. So notice what happens when we plug in x equals 2. This is going to turn into 0, that whole thing, because 2 minus 2 is 0, and 0 times anything is 0. So that piece will disappear. So we'll plug in the x equals 2. Right? So we plug in the x equals 2. We have 5 times 2 squared minus 5 times 2 plus 5. We'll simplify that in a minute. And over here, 2 squared is 4. 4 plus 1 is 5, so we have 5a. The other piece turns into 0. Okay, what do we have here? I'll write the plus 0. What do we have here? 2 squared is 4. 4 times 5 is 20. We have 20 take away 10 plus 5. So that's 15 equals 5a. Right? So in other words, a equals 3. All right. Now, okay, this is where we're going to do something a little bit different this time. I'm going to distribute here, distribute here, distribute here, distribute. So we're going to rewrite the equation as 5x squared minus 5x plus 5. This is what we do if we get down here and choosing nice values don't work very well. We equate the coefficients of like powers and write a system of equations or a combination of that. Okay, because we've already used one nice value. Let's see, where was I? I was right here. Okay, so back to example 5. So we are multiplying out the right-hand side now. So ax squared plus ax plus, and then when I distribute over here, look at what has to happen. I have bx squared, and then I have minus 2bx, and then I have plus cx, and I have minus 2c. All right, that's what we have. Now we're going to equate coefficients. So a plus b, those two terms that involve x squared have to add up to this one. So in other words, a plus b has to equal 5. But I already know that a is 3. So the x squared terms have to add up to the same thing that we have on the left. So a plus b has to equal 5. But we know that a is 3. that would mean b is 2, right? This is what they mean by equating coefficients. Okay. Now I can either use the fact that a minus 2b plus c equals negative 5, or easier yet, let's do this. Did I lose somebody somewhere? Yeah, I kind of made a mistake here. Let me rewind right here, this one right here. When I distributed, I had ax squared, and that should be plus a. Yep, that was kind of problematic. So what do I have? So equating constants, this constant and that constant. So those two terms that don't involve the x have to add up to 5. So in other words, a and negative 2c have to equal 5. A plus negative 2c, or a minus 2c. But we already know that a is 3. Okay. So if we subtract 3 from both sides, we get negative 2c equals 2. So c equals negative 1. Now I have them all, a, the b, and the c. So what do we got? When it's all said and done, let me go back up here just a little ways. We've got the fraction right here, 5x squared minus 5x plus 5. You can see it on your paper. 5x squared minus 5x plus 5 over x minus 2 times x squared plus 1 has to equal a, which is 3, over x minus 2, plus bx plus c, bx plus c, replace the b with the 2, the c with the negative 1, over x squared plus 1, and that is our answer to this problem. Okay, next page. We're almost done. We're going to talk about what happens if the denominator has repeated irreducible quadratic factor. In this case, solving is a mixture of case 2 and case 3. We're going to talk about how this works. But in these last two examples, we're just going to write out the partial fraction decomposition with the a, the b, and the c in place, but we're not going to solve for the a, b, and c, right? Or however many letters we have. But we're just not even going to solve for them. So I wish that dot weren't there. I'm just going to replace it with an equal sign. So I'm just going to write out what this would look like. Notice what I have. I have a linear factor. So that's going to be a constant over x, and it's not a repeated factor. But then I do have a repeated quadratic, a repeated irreducible quadratic. So what I have to have is I have to have two fractions for that. I have to have a bx plus c, because the irreducible quadratic has to have a linear top, not just a constant, but a linear top. Okay. But because that's a repeated factor, I have to have a second fraction. So my second fraction is going to be dx plus e. We'll just go through the alphabet, divided by x squared plus 1 squared. And we're done. It asked us not to solve for the a, the b, and the c, so we're not going to do that. We're just going to write out what it would look like, call it good, and we're done. And then the very last example right here, we're going to write out the partial fraction decomposition with the a, b, c, however many letters we need, but we're not going to solve for those constants a, b, c, etc. Okay, so this is going to be a big one. So we're going to write small. I need you to write small to fit it all in. So we have a linear factor here. X minus 2 is linear, but it's going to require 3 fractions because it's to the third power. Oh, and keep in mind that we can only do this if the fractions are proper. Let's go back up to this one. This is degree 4. Down here, this would be degree 5 if you multiplied it all out. I need you to think about that. This one that we're working on right now, the numerator is degree 2, the denominator is way bigger degree than that. So no problem with these being proper fractions. So we have to have an a over x minus 2 plus a b over x minus 2 squared plus a c over x minus 2 cubed. I'm not sure we're even going to be able to fit this all in one line because it's going to be so long. Then we have to have a fraction for the x plus 4. So we have to have a d over x plus 4. And then notice this is an irreducible quadratic, but it's repeated. So I'm going to have 2 fractions for that. Okay. And the top of those fractions have to be linear, ex plus f over x squared minus x plus 1. And then we are going to make it EFG. So we have gx plus h over x squared minus x plus 1 squared. And we're done. That's what the expansion would look like, but we asked you not to solve for the constants a, b, c, d, e, f, g, h. And that is it for this section.